Let us resume. So welcome back again. Today we are very happy to have Professor Zoran Vondracek from University of Zagreb, Croatia. So the second talk is about the potential theory of stochastic processes with jump kernels degenerate at the boundary. Please welcome him.
Thank you. Welcome back. Happy that now we have Professor Colloquium in the audience, whom I known for more than 15 years. And I'm also happy to have Professor Funky Kim, my collaborator, who will take your questions. Okay, so this is some sort of continuation of the previous talks where I introduced the basic concepts. In this talk, I will concentrate on jump kernels which are degenerate at the boundary, and I will explain what I mean being degenerate at the boundary. But the main topic are similar as the previous talks. I will concentrate on the boundary Harnack principle and the green function estimates. So here is an outline. So first I will give introduction and motivation. Then I will talk about the jump kernel decaying at the boundary. And then the next part is the jump kernel blowing up at the boundary, and if I have enough time, then I'll compare the decay case and the blow up case. So here is the introduction and motivation. So let me discuss briefly what is a fractional Laplacian in an open set. Take D, be an open subset of Rd, alpha is between 0 and 2, and I include 2 now. I consider the isotropic alpha stable process killed upon exiting D. Sometimes I will also include the case of Brownian motion. So the corresponding Dirichlet form in the case of alpha strictly less than 2 is given as follows. So this is the same integral that we saw in the previous talk, but this time, since we looked at what happens on D, we require that U is in the domain form, but that it is 0 in D complement. So if you take into account that in this integral that U is 0 in D complement, you end up with an integral over D and integral over D. This remains when Y and X are in D. When Y and X are both in D complement, there is nothing. And one is Y, one is in D, and one is in D complement. What you have is the integral over D, Ux squared, some function kappa, which is given by this expression. And this function kappa is called the killing potential. And in case D is C11 open set, it is known that this killing potential is comparable to the distance of the point X to the boundary to the power negative alpha. And the infinitesimal generator of the corresponding semigroup is given by the following principal value integral. So we integrate uy minus ux, x minus y to the negative d alpha minus alpha over d, and then you subtract the killing potential multiplied by the value of the function at x and in d. And this operator is usually called the alpha half fractional Laplacian with 0 exterior condition because of that. And you write it as the negative Laplacian to the power alpha over 2 restricted to D. And some people call it the restricted fractional Laplacian, RFL. So this is one way how to define fractional Laplacian in an open set. And as I mentioned in the previous talk, at the end, the sharp two-sided green function estimates were obtained by Chen Song and independently by Kolchitsky, and this is the expression for the sharp. So the right-hand side are sharp two-sided estimates. So you have the risk kernel here, and then you have the boundary behavior, which is governed by the power alpha over 2. And the boundary Harnack principle holds for non-negative harmonic functions with the exact decay rate is distance to the boundary to the power alpha over 2. Okay, So one can regard this restricted fractional Laplacian as a Schrödinger perturbation of the regional Laplacian in D. So the regional Laplacian is defined as the operator L sub alpha ux, u at x, is simply the principal value integral over D of this expression. And if you compare with this formula, then this part is simply the regional Laplacian. And to get the restricted fractional Laplacian, you subtract the killing term. The regional fractional Laplacian is the restricted fractional Laplacian is the regional fractional Laplacian minus kappa x ux. And this is a critical perturbation. And I don't want to explain what critical means here. And the operator L alpha is called sometimes the censored fractional Laplacian or the regional fractional Laplacian. And the corresponding stochastic process is the so-called censored stable process, which was introduced in the famous paper by Vondracek and Chen, 2008. Now, what does the censored stable process do? Here is D. You start running your isotropic stable process. When it exits D and you kill it, the corresponding infinitesimal generator is the restricted fractional Laplacian. But now, for the censored process, you pretend that nothing happened. You just censor the jump. You disregard it and you start the process afresh. And it goes afresh. It wants to jump out, but you censor the jump and you continue. And the infinitesimal generator of the censored fractional Laplacian is precisely this censored. Whether the censored process is precisely this censored fractional Laplacian. Okay, so this is another way you can define the fractional Laplacian in an open set. And there is a third way. You can look at the fractional power of the restricted fractional Laplacian. Take beta between 0 and 2. 2 is included, and gamma between 0 and 1. And consider the fractional power. So you take negative delta to the power beta over 2 restricted to D. So this is the restricted beta half fractional Laplacian. This is certain operator, and you take the gamma power of this operator. Anyway, you find you know it. So when beta is 2, this is usually called the spectral fractional Laplacian. You take the Dirichlet Laplacian and take it to the gammath power. Probabilistically, this means the following. You take the beta stable process, something which moves inside, and you kill it when it exits D. So you look at the killed beta stable process. And then you subordinate it by an independent gamma stable subordination. Basically, it means you take only certain points. And this is the process you obtain, and the infinitesimal generator of that process is precisely this operator. Again, you take the beta stable process, you kill it, and then you subordinate it by an independent gamma stable subordinator. And you call this subordinate killed stable process. And beta is 2, it's a subordinate killed Brownian motion. So some aspects of this operator, in case, okay, one thing I didn't say. Everything I'm going to say in this talk is joint work with Monkey Kim and Renming Song from the US. Some aspects of this operator, in case when D is an open C1 unset, and in particular, which properties of this new process depend on beta and which on gamma were studied in these two papers. One is in transactions when beta is 2, and the other is potential analysis when beta is strictly less than. So we were interested what happens with the potential theory of subordinate killed beta stable process. But now there are two parameters, beta and gamma. And we note alpha, let alpha be the product of beta and gamma, so this is a number between 0 and 2. And we prove the sharp two-sided green function estimates. And there are two parts. One is x minus y to the negative d plus alpha, which is sort of interior part. And this corresponds to the alpha stable process because beta times gamma is alpha. But then the boundary part depends only on beta. It doesn't depend on the subordinate of gamma. So the power is beta over 2. So if you look at this one and think of alpha being beta, then you have beta to the power beta over 2, but here you have negative d plus beta when you look at the killed beta stable process. But here the situation is different. This power, this exponent is different than that one. And you can rewrite this, and I'll explain why I do it later. So as a minimum of distances to the boundary, and then the maximum of distances, because if x is closer to the boundary, then the minimum is x, and the maximum is y, and vice versa. Makes no difference. The Dirichlet form of this process is given by the following expression. It's the double integral of uy minus ux squared over certain jump kernel, jxy. And then you have integral ux squared over certain killing function, kx. And one can show this killing function is again comparable to the distance to the boundary power negative alpha here. Okay, so far so good. There were no surprises at this point. The most interesting ingredient is this jump kernel, which has a rather unusual two-sided estimate. In case beta is 2, this is something which was done in this first paper. At the time, we were not really aware that something strange is going to happen later. This is what we expected, that this is x minus y to the negative d minus alpha. This is the jump kernel stable process, alpha stable process. And then you have the boundary part, which depends on the distance to the boundary. Because when beta is 2, the underlying process, which is subordinate, is the Brownian motion. So you have the Brownian motion boundary behavior. So it does not depend on gamma except through this alpha, which is beta times gamma. Okay, and you can again write this as the minimum distances, maximum distances. Now, when beta is strictly less than 2, there was a surprise. The jumping kernel was comparable to this expression when gamma is between 1/2 and 1. So there is only the minimum of distances, maximum is missing. When gamma is between 0 and 1/2, and then you have both minimum and maximum, but with different powers. Beta over 2, beta over 2, 1 minus 2 gamma. And when gamma is 1/2, there is certain phase transition. You have this part. When gamma is 1/2, that's precisely beta over 2. But then you have the logarithmic correction here. And so when gamma decreases from 1 to 1/2, you have this. And then when it's equal to 1/2, you have another term. And when it goes below, then you have both terms with a certain power. Okay, so we can write this jump kernel as x minus y to the negative d minus alpha times certain function script b. So define script b as the quotient of j and this thing. Then the red part here is comparable to this function dxy. So we see that the jump function can be written this way with this part b, which is comparable to this red part, depending on where gamma is. But there was another very surprising fact in the second paper, and that was that when beta is 0, 2, the boundary Harnack principle holds when gamma is between 1/2 and 1. But it fails when gamma is less than or equal 1/2. although Carlson's estimate holds true. And that's essentially the first example of processes where some sort of natural processes when the boundary Harnack principle fails.
What is boundary Harnack principle?
I explained in the first talk. So I'm not going to explain. That was the purpose of the first talk.
What about colors?
I explained Carlson as well. Okay. When beta is 2, and then the boundary Harnack principle holds for all gamma. That was proven in the first of these two papers that I mentioned. And when true, the decay rate of harmonic functions is the distance of the power beta over 2, independent of the subordinator. It just depends on the underlying process. But it may not be true. Okay, so this slide actually motivated us to look at this more abstract version of the boundary decay. We try to understand why this happens. So I think that now we understand more why this happens. Maybe not everything. So now I will talk about the jump kernel decaying at the boundary. So here's the setting. Okay, the state space is the upper half space RD plus. So the points are written as x tilde xd, where xd is a vertical component which is strictly positive. Alpha is between 0 and 2. You may ask why we work with RD plus, and the answer is simple because we didn't know better. That was quite challenging. Now we know a little bit more, but at the moment we stick to the upper half space. The jump kernel will be defined as the product of the isotropic alpha stable jump kernel times some function b, depending on two variables. This function b somehow should encode the boundary behavior. That's why it's called b, but that's not quite correct. I will not call it the boundary part, just b. So in case when b is strictly between two positive constants, this is well studied and can be viewed as a uniform elliptic condition for non-local operator for fractional function. Basically means that this jump kernel is comparable to the jump kernel of free stable process. And in that case, one introduces the pure jump Dirichlet form this way, possibly with certain killing, and shows that there is a corresponding Feller process. And so this has been studied for many, many years. There are many different results. This is sort of well understood. But motivated by the jump kernel of the subordinate killed stable process, we try to develop the theory where the function b depends on the distance of x to the boundary, which is the xd component, yd, as well as the distance between points x and y, and decays at the boundary. So this is the content of the following three papers, which this one appeared just last month, although it has been done for 4 years already. The second one will appear, and the third one will also appear. I mean, the second and third are all mine. So we need some assumptions on the function b. So here are the assumptions. First assumption that b is symmetric because we want to deal with a symmetric process. So that's clear. Second assumption, we need that alpha is bigger than or equal to 1. And it says that there exists a constant theta bigger than alpha minus 1 and c bigger than 0, such that the difference of bxx minus bxy is bounded from above by this expression. So this is some sort of Hilbert continuity of the function b in one variable. And I'm not going to explain in this talk why this is needed, but it is essentially needed to be able to handle the infinitesimal operator of generator of this process. You need some extra consolation coming from this power theta. A4 has two parts. One is scaling. We want the jump kernel to scale the same way as the jump kernel of the stable process, which means that this is the assumption we put on the function b for each a bigger than 0. And then we need horizontal translation invariance. When d is bigger than or equal to 2, for all xy in Rd plus and all z tilde in Rd minus 1, when you shift x by z tilde 0 and you shift y by z tilde 0, nothing happens. So this is horizontal translation invariance because we want the resulting process to be horizontally translation invariant. Okay, so you may wonder where is A3? A3 needs a separate slide. That's the most important assumption. We assume that there exists constant c bigger than 1 and 4 parameters, which are all non-negative. Beta 1 is positive, if beta 3 is positive, beta 2 is positive, beta 4 is positive. Such that the function b is comparable to the function b tilde, where b tilde is defined in the following somewhat complicated way. So you should concentrate on the blue part because everything depends on the blue part. This black part with powers beta 3 and beta 4 are logarithmic corrections. So why do we look at this? Because if the jump kernel that I showed before coming from the subordinate kill beta stable process is very similar. You have the distance to the minimum distances to the boundary divided by x minus 1, minimum 1 to some power. Here was several powers, so we put beta 1. We have the similar thing with maximum. Here beta 2 is 0. Here beta 2 is 0. Here is this exponent. And then this logarithmic term corresponds to this logarithmic term. And the last one appeared in some other example that I did not show you this time. So for this stuff, you can simply forget about beta 3 and beta 4. Everything depends on beta 1 and beta 2. So for us, that was a very general function b, which shows a decay. Of course, it decays at the boundary because these powers are non-negative. Only beta 1 and beta 2 are 0, so this is just 1. And notice that larger beta 1, this is sharper decay at the boundary. Okay, now let me describe the killing potential. To every parameter p, which is in the interval alpha minus 1 plus alpha plus beta 1, the associated constant, which depends on alpha p and of this function script b, which is strictly positive and finite, in the following semi-explicit way. Don't try to understand that. I will come to that later. So you have the function b here, you have parameter p, and you have alpha. Ed is the vector, unit vector in the horizontal, in the vertical direction. The point is that this function is a function p strictly increasing, continuous, and at alpha minus 1 plus is 0, which is the limit when p goes down to alpha minus 1 plus, and when p goes to alpha plus beta 1, this function goes to infinity. So this means that you give me a constant kappa, which is strictly positive. I will find p in this interval such that your kappa is equal to this constant. So I cover all positive constants kappa with this expression. And I define the killing potential kappa x is this constant multiplied by the distance to the boundary to the power negative alpha. So this is the critical killing for this isotropic, a stable alpha stable case, and I multiply by this constant. And when alpha is between 1 and 2, we allow that kappa is identical to 0. Otherwise, when alpha is less than or equal to 1, I require that kappa is strictly positive. Now I introduce the usual, in the usual way, I introduce the Dirichlet form. The domain is the closure under this, this norm, Hilbert norm, and this is the regular Dirichlet form on L2, and then I introduce the killing the usual way, change a little bit the domain, and then EF is the regular Dirichlet form again on L2. So this is the standard thing how to get regular Dirichlet form. Under assumptions A1 to A4, there exists a symmetric scale invariant and horizontally translation invariant Hunt process. Hunt is a special case of strong Markov process. which I will denote by y kappa, associated with this regular Dirichlet form. So there is a process with the jump kernel that I described. And the infinitesimal generator of this process is given, in fact, okay, so forget about what I said. Introduce the operator L alpha super B as the principal value integral over RD plus uy minus ux jump kernel xy dy. So this is this principal value jxy is b function divided by x minus y to the power of d plus alpha. And this is well defined whenever the principal value makes sense. And now the infinitesimal generator of the process is obtained from this operator, and you subtract kappa x ux, the killing term. Kappa x is simply C alpha PB. Again, for each positive constant here, kappa, there is a P. So the operator depends either on the constant kappa coming from the killing or this P, which is in between alpha minus 1 plus and alpha plus beta 1. And then at least formally, the form is given by this in L2. So this LB is the infinitesimal generator of the corresponding semicolon. So let me now explain this C alpha PB, which is sort of mysterious, this constant. How did we come up with this constant? Okay, so this constant, when B is simply identically 1, appeared already a long time ago in the paper by Bogdan, Burji, and Chen, where they studied the censored process. And so we modify this. And the reason why this appears is sort of very simple. Look at the function GP, y, which is the distance of the point y to the boundary to the power p. And take this operator L alpha and compute this operator on GP. And this can be done explicitly. It's not straightforward, but not too difficult. And what it turns out is that this operator is some sort of alpha fractional Laplacian. So it decreases the power by alpha, which is here. And what comes out is this constant. So this constant comes out when you compute this, the infinitesimal generator on the distance function to the boundary. So you can say that this operator annihilates the distance function to the boundary. So we have a function which is distance to the power p. We compute the infinitesimal generator and then we get 0. So this is harmonic for this operator. Okay, so YT is the process. This I already discussed. Special case, when Bxy is identically 1, there's no boundary term, and I take P to be alpha over 2, this parameter. Then Y is precisely the isotropic alpha stable process killed upon exiting RD plus. And the green function estimates we saw before. So this is the Rees kernel, and then we have the distance and distance to the power p, which is now alpha over 2. This is what I showed you on one of the first slides. When alpha is bigger than 1 and less than 2, and b is identically 1, the corresponding process is the censored alpha stable process. And the green function estimates is exactly of this form, but this time p is alpha minus 1. This was proved by, I think, Banke Kim and Janshin Chen for DC11, long time ago. Okay, so here are two results that we managed to prove. Assume A1 to A4, kappa, the killing function, is a constant multiplied by xd minus alpha. That's okay. One thing that I should emphasize, the killing function, it's always xd to the negative alpha. The only difference is what constant in front of this function you take. Everything depends on the size of the constant in front of this function. and P is between alpha minus 1 plus and alpha plus beta 1. Dimension is bigger than 2 in this theorem. Then the process admits a green function, which is continuous on Rd plus minus x, a regular harmonic with respect to y in Rd plus when you subtract a small ball around x. And moreover, gxy has the following estimates. If P is smaller than alpha plus 1/2 beta 1 plus beta 1 minimum beta 2. Okay, notice if beta 1 is less than or equal to beta 2, then this expression is beta 1, so we cover all range. Then this is the estimate. But there is nothing surprising here because this is more or less the same as this one. So just P and P. Now the question is what happens when beta 2 is smaller than beta 1? Okay, and this can be written as minimum or maximum. So first we take P to be on so here's the open interval. And the boundary case, P is alpha plus beta 1 plus beta 2 over 2, then we have a logarithmic correction. Here this exponent beta 4 appears, but even if beta 4 is 0, there is still 1, so we have a logarithmic correction. And if P is between alpha plus beta 1 plus beta 2 over 2 and alpha plus beta 1, then we have something which looks like this. Minimum to the power P, but maximum is on some different power. Yeah, okay, forget about logarithm if beta 4 is 0. So this is sort of weird and very strange, and you can think of this as anomalous behavior of the green function. So this is the usual way how the green function estimate should look like. But under our settings, they can be sort of different. I'm not going to go to any details of the proof because that would need maybe like 3 or 4 such lectures. And then we also looked at the boundary Harnack principle. So DWAB is certain box. So that's how does this look there? It's nice. This replaces the ball near the boundary because it's more convenient. So this is 5D minus 1. Here is the vertical component R. You take some point W at the boundary, and then you look at the box. So this size is A, and this height is B. So this is this box. This is essentially a cylinder because this part is dimension 3 or more circles. Something so that's they call it the box, but it's actually a cylinder more than 2 dimensions. Okay. And here's a theorem. Assume that P is between alpha minus 1 plus and alpha plus beta 1 minimum beta 2. Now, if beta 2 is bigger than or equal to beta 1, this covers all range of P. And then the claim is that the boundary Harnack principle holds with the exact decay rate, which is the pth power of the distance to the boundary. So this is a consequence that you have a real boundary Harnack principle without the decay rate, but it's not so important. What is important to see here is that suppose that beta 2 is bigger than beta 1. Then your P is between alpha minus 1 plus and alpha plus beta 1. Beta 1 can be arbitrarily large. There's no restriction on beta 1, which basically means that you can your P, corresponding P, can be arbitrarily large. So you can cook up Hunt process, which has killing, which has harmonic functions which decay at an arbitrarily large rate. Okay. And there is a failure of boundary Harnack principle. Now, if beta 2 is smaller than beta 1 and P is between alpha plus beta 2 and alpha plus beta 1, then the non-scale invariant boundary Harnack principle is not valid for Y. And I will skip what scale invariant means that the boundary Harnack principle is not valid. Okay, so that is all I wanted to say about the decay case. Now let me move to the blowing up at the boundary case. So first, how can we cook up processes with jump kernels blowing up at the boundary? How do they appear naturally? So that's the first question. We need some examples. We take, again, an isotropic stable process in RD, and instead of doing this mathematical part, let me draw a picture. So here is boundary, here is the upper Cal space. You start the process, it moves and then jumps out. It moves, then jumps in. And what you do, you simply forget about this part, remove it. And you continue the process here, like this. This part is just shifted there. So basically, you erase from the trajectory everything which is in the lower Cal space. You can do it by using this additive functional, which measures time in the upper Cal space. You take the inverse, and then you simply time change the original process. You get the Hunt process RD plus, which is called a trace process. Simply forget, you don't see what is happening below this line. Okay. So now suppose that X jumps out of RD plus from the point X and lands. Let me go to the picture again. So this start the process, and at point X it jumps out and lands somewhere here. This is Z. Okay. Starting at Z, how is it going to enter the upper Cal space? Moves, and then it jumps up. But we know how the process which starts from somewhere exits some state space. We know the distribution. This is given by the Poisson kernel, that part. And it will enter, starting at Z, it will enter the upper Cal space RD plus according to the Poisson kernel of the lower Cal space. C is the starting point, and the density is given by PRD minus Z1. So we can call this Poisson kernel of the lower Cal space the return kernel. This is how it returns to the upper Cal space. So this implies that if X jumps out of RD plus from X, as in this picture, it returns to RD plus according to the following kernel. So this is the jump kernel, jumping out from X, landing in Z, and this is returning from Z to Y. And you integrate over all Z. So this is easy, sorry about that. And JXZ is the usual stable jump kernel up to some constant, but I said I would disregard constants. Okay, so this means that the trace process, so what you see when you observe it in the upper Cal space, has the jump kernel, the original jump kernel, J intensity of jumping from X to Y, but there is additional intensity. From X to Y, if it went to the lower Cal space and returned to Y here. So that's the new jump kernel. Okay, so this part of the talk now is based on the following two papers, which are quite rather recent. This was done in summer and already appeared, and this is still being reviewed. Also with Anke Kim and Min Song. So let me discuss the resurrection kernel. So we are not satisfied with the return kernel, which is the Poisson kernel, but we want to cook up something much more general. So the function P from RD minus times RD plus into 0 infinity is a function such that for Z in RD minus PZ dot is a probability density on RD plus. And we think of PZY as a return kernel. So this describes how the stable process, when it exits the upper half space and lands in Z, will return to the upper half space. And then we define Qxy as on the previous slide, and define the jump kernel Jxy is lowercase jxy, which is x minus y to the negative d minus alpha, plus this Q, which we call the resurrection kernel, because this is how the process is resurrected when it dies. Okay, we would like the resurrected process to be symmetric, to have the scaling property, and to be invariant with respect to horizontal translation. And so we need from Q to have this scaling property and this horizontal translation, and these properties will depend on the return kernel P. The return kernel P is the only thing which is given to us. And we assume that the return kernel is given by this expression. Okay, the reason why we assume this is because we looked at this very carefully and decided this is the correct way to look at it. And the function psi here is a function from 2 infinity to 0 infinity, which satisfies the condition that I will specify below. You may ask why 2, because this argument is always larger than 2, so you don't need the function. Okay, so there are some special cases. When psi of t is 3 to the alpha over 2, then PZY is precisely the Poisson kernel of RT minus. And when CT is 1, then PZY turns out to be JZY normalized. So you return from Z to Y using the same jumping kernel that the process uses, which is normalized. And such cases related to the Neumann, non-local Neumann, non-local Neumann boundary value problem, which was studied by Baldinacci, Degenerate, and somebody else also done. Okay, so the condition on the function psi, we take two constants, and which are strictly bigger than negative infinity, less than 1 minimum alpha. This condition is because of integrability. And we assume that psi satisfies the following weak scaling condition. And so this is the assumption of psi. Now we have to check that psi has, that Q has these properties. So when psi is given, when P is given by this expression, the resurrection kernel is given by this formula. And it is straightforward to check that Q lambda x lambda y is given by this, and it is horizontally translation invariant. One thing which is not obvious, and it's actually far from obvious, that Qxy is symmetric. If you look at the right-hand side, the x and y do not appear in the symmetric way. So the first thing we have to show is that actually the resurrection kernel is symmetric. It is indeed symmetric. So I will not go into that. And note that we can write Jxy was defined as the lowercase plus the resurrection kernel. We can factor out the Jxy. What remains is 1 plus Qxy over Jxy. This parenthesis I will denote by script bxy. So now I have the same form of the jump kernel. Jump kernel is a stable kernel multiplied by some function. Okay, so now I want to show that the jump kernel, J, actually blows up at the boundary. And this is due to Qxy, because Jxy is x minus y to the negative d minus alpha. This doesn't blow up at the boundary when either x or y go to the boundary, stay bounded. So the blow up is due to this resurrection kernel. So let psi1 be this integral. Essentially, you can forget about it, because if psi is the power function, then psi1 is the same power function. But now we have a theorem which says the following: if minimum of distances is bigger than x minus y, so you are in the interior of the space, then Qxy is given by this expression. So this is nothing new. What is interesting when one of these 2 points is closer to the boundary than to the other point, then QXY is how do we say this? Comparable to x minus y negative d minus alpha c psi 1 x minus y squared over x dy d. In particular, when gamma 1 is positive, then you can replace psi 1 by psi, and when gamma 2 is negative, then nothing happens. You have x minus y negative d minus alpha. So this is perhaps a little bit difficult to understand. So let me give you an example. Take gamma less than 1 minimum alpha and delta real number. Suppose that psi t is t to the gamma log delta t. So it's basically a power function up to some logarithmic correction. So this is the return kernel in this case. And so this is when you are in the interior, we are close to the boundary. QXY is comparable to the jump kernel of the process. So when gamma is positive, this is x minus y squared over x divided to the power gamma. And suppose just that delta is 0, so there is nothing. And you can see that when x or y go to 0, xd or yd goes to 0, this blows up as the power 1 over xd to the power the gamma. And this shows that this jump kernel blows up at the boundary. When gamma is 0, and suppose delta is 1, delta is also 0, but suppose that you have just a constant, then you have a blow up which is of the order log x minus y squared over x dy d. So this corresponds to this my second example. So in any case, this should convince you that there is a blow up, and we can get blow up as large as we want, or up to 1 minimum alpha. Okay, how much time do I have now?
Was come from
2 minutes, right?
Fine.
5 minutes. Okay, so that's the. Since I don't have much time, I'll go very quickly. Now we have a general framework, which is very similar to the one that I explained for the decay. We have these 3 conditions on the function b, a1, a2, and a4, which are the same as in the decay. The only difference is that the condition a3, so we assume that we have a function which satisfies certain scaling condition, and let me skip Matuszewska, and then b is of this form. B function is comparable to the function phi x minus y squared xd over yd. And this is of course motivated by this result. So in case when p of t is t to the beta, and beta is between 0 and 1 minimum alpha, then one can show that this b is actually comparable to the distance to the boundary to x minus y minimum 1 to the power negative beta. This is very similar to the decay case, but in the decay case, the power was positive. Here, the power is negative. And then we construct the Dirichlet form in the usual way, the process in the usual way, the constant coming in front of the killing form is exactly the same constant, so there's the same formula. So let me skip all that. The operator is the same. So everything is the same except the jump kernel is different. The D part is different. It blows up at the boundary. And we proved the boundary Harnack principle, but now the P is restricted to alpha minus something positive. So now we have smaller range of parameters P. And then we again prove the boundary Harnack principle, this time for everything with the decay, which is of the order distance to the power P. And we have the green function estimates, which are now when d is bigger than alpha of the usual form. And these are estimates for d is 1, but since I haven't talked about that, I will skip that. And I think that I don't have much time, so I skip this. There are 2 more slides. Thanks. Samida.
Questions or comments?
Yes.
I have two questions about the presentation. First, the first one is the boundary means the recurrent state, the set of recurrent is the boundary means the recurrent state. Because the boundary, the so some stochastic process only only works on the boundary. So I thought that the
I'm not sure if I understand your question, but the process does not live on the boundary. Only the jump kernel either decays at the boundary or blows up at the boundary. So boundary actually is not part of the state space. The state space is the open up half space, which is the boundary just is there, but it's not part of the state space for in this case. So we get some results when it is, but here not. Was this your question?
Yes,
Okay.
thank you. And the second one is the kernel. Is there any reference that trying to use the kerning process for modeling on phenomena like the physics? I thought because that the jump kernel is the similar to the phenomena some quantum or like social science because they
Can you?
The fractional Laplace like alpha is 1/2.
yes.
The what you call this relativistic.
Relativistic?
Yeah, I think that's what he meant. Maybe. So your question is
Is there any trying to use the kerning process for modeling?
How kill process for modeling? I'm sure the people use it because the kill process is just the process more or less restricted to a certain open subset. And if you don't want to run your process, or you, I mean, most physical situations are restricted to some bounded sets anyway. And then, but okay, that you don't, okay. Maybe it's better to call the kill process part of the process. So just look at the part of the process in this restricted set that you have. I think that all modeling must use this process because you cannot use the whole process to model things because it lives in RD. Any physical purpose you have to restrict that, I would say. So I would say yes, but I don't know, the reference.
Thank you for answering the question.
Like the fractional heat equation in a bounded domain or a Boltzmann equation in a bounded domain. You always have some jumps outside the domains. Within the killing process.
Yes.
I have one question. In the chapter 2, maybe chapter 2, jump kernel decaying that part. In there, can I see that from beta 1 to beta 4?
Go to the slide and then we'll. Oh, this is still lower.
In there, yes, when we choose the region of P from beta 1 and beta 2.
No, P depends, the region of P depends only on beta 1. That's another thing. P is always between alpha -1 plus
Yes.
and alpha plus beta 1. The region of P depends only on beta 1. It does not depend on beta 2.
Then,
That's another thing which is at the first sight weird, but there is a reason for that.
then can I see the beta 1, that full equation about beta i's? Yes. We separate the equation.
In the beginning, where I have this,
Yeah.
So the region of parameter P, the strength of killing, so this depends only on beta 1. The results that I have about the green function and the boundary Harnack depend on beta 1 and beta 2.
Okay.
Okay, in the green function estimate also beta 4 appears, but these two logarithmic terms are just proving the things much more complicated, but there is,
Okay.
you can just forget about that.
Thank you.
Okay, disagrees.
I mean, the range of the P's depends only on beta 1, but the actual value of P depends
On the whole
that
field.
whole
Okay, that depends, of course, the value of P,
depends on this expression, yeah.
right, because the constant C depends on the all of B. It just not okay. So there are two things. So B, there are two functions B, script B, which actually goes into the jumping kernel.
Yeah.
And this script B is comparable to B tilde, which depends on beta 1, beta 2, beta 3, and beta 4. But if you look at the constant C, this constant depends on the actual script B function.
Thank you.
So you actually cannot compute it, especially so easily. You cannot compute it at all.
Thank you.
Any other questions?
Yeah,
I have one more question about the green function, but in some partial differentiation, the green function is for solving some equation. But I saw the presentation, but there I couldn't find the equation for solving by green function. Is there any what kind of equation we use for green function in the
it's all the same. You take the infinitesimal generator and look at it, let me call it L. You solve LU is 0 in the state space, and you want U to be equal F inside. And then the solution is the green potential of the function. That's always the case.
Okay, thank you so much.
Yeah.